Welcome to The Explainer. So think for just a second about every streaming movie, every single video call, every email, and every photo you've ever uploaded. They all kind of feel like they just live out there in this invisible cloud, right? But the reality is actually beautifully physical. The vast majority of our entire global data network is powered by microscopic beams of light, just shooting across oceans and continents at literally unimaginable speeds. Today, we're going to pull back the curtain on the invisible backbone of our modern world to understand exactly how this all works. Here's our roadmap for today. We're going to start with the anatomy of fiber optics, look at the speed of light, dive into total internal reflection, compare single versus multi-mode cables, and wrap the whole thing up with the fiber advantage. Let's get right into it. Section 1, Anatomy of Fiber Optics. Because, before we can even talk about the light itself, we really need to understand the physical vessel that's carrying it. Okay, let's dive into this and take a look at this elegant design. It's essentially just an incredibly simple concentric cylindrical structure. Basically, cylinders nested inside of other cylinders, kind of like an onion. The absolute center is where the real magic happens. That's where the light pulse is actually guided. But to keep that super fragile glass from shattering underground, it needs some serious armor. Breaking down those nested cylinders, we basically have four main components. At the absolute center is the core, a tiny, tiny cylinder of glass or plastic. Surrounding that is the incredibly crucial second layer, the cladding. We'll get into the exact physics of it in just a minute, but the cladding acts as a literal barrier for the light. Moving outward, the buffer is there to defend the glass from moisture, and finally, that tough outer jacket just holds the whole shebang together. Now that we know what the cable physically looks like, let's move right along to Section 2. The speed of light. We're shifting focus to the mind-bending physics of how data actually moves. To really grasp fiber optics, we have to talk about the index of refraction, or the IOR. I know, it sounds super intimidating, but honestly, it's essentially just a cosmic speed limit. It tells us exactly how much a substance bends, or refracts, light. The equation is n equals c over v, which simply means you take the speed of light in a perfect vacuum and divide it by the speed of light pushing through a specific material.
Now, what's really interesting about this slide is when you apply that math to the real world, things get wild. In a pure vacuum, light blasts at roughly 300,000 kilometers per second. Air barely slows it down at all. But look at the bottom row there. The glass we use in our fiber cores has an index of refraction of 1.5. That physically slows the light down to 200,000 kilometers per second. Realizing that every single internet search you do relies on this, and actually feeling that physical drag that glass puts on light, that is pretty profound.
Which brings us perfectly to Section 3, Total Internal Reflection. This is the absolute core phenomenon of theoretical physics that actually makes this whole system possible. Notice the contrast here. On the left, you've got a standard, formal textbook diagram showing light bending as it enters water. But right next to it, you can see someone's real-world study notes writing out Snell's law. This equation links the angle of incidence right back to those refractive indexes we were just talking about. And it begs a really great question. What happens if you bend light so much that it can't even cross the boundary at all? So the crucial point is total internal reflection. If light hits that boundary between the core and the cladding at an angle greater than what engineers call the critical angle, it gets completely rejected. Because the core deliberately has a higher index of refraction than the cladding, the light just bounces perfectly back into the center. It gets hopelessly, wonderfully trapped, endlessly bouncing down the inside of the cable, carrying your data across oceans. All right, with the physics established, let's step into Section 4, Single versus Multimode. We are moving from pure theory right into the actual engineering of the core. Engineers basically design two distinct flavors of fiber cables, single mode and multi-mode. Single mode has an incredibly tiny core. We are talking about a radius of around 3 micrometers. It only allows one single path of light to travel. Multi-mode, on the other hand, has a much wider core, allowing multiple paths, or modes, of light to travel at the exact same time. The trade-off? Well, multi-mode is way easier to connect and great for shorter hops, while single mode is the undisputed king for ultra-long-distance, huge bandwidth hauls. You can immediately see the physical difference in these designs here. The single-mode fiber shoots a super clean, laser-focused zigzag path straight down that tiny core. Multi-mode, however, has all these bouncing, intersecting rays traveling at a bunch of different angles simultaneously. Like I said, it's more forgiving to connect, but all those bouncing pads mean the light pulses can actually start to spread out and blur together over long distances. Achieving that laser-focused single-mode transmission requires incredibly strict parameters. The core has to be microscopic, and there's a very specific mathematical property known as the V number that absolutely must stay under 2.405. If engineers can hit this exact target, they achieve zero dispersion, meaning the light pulses don't smear together, which allows for just massive bandwidth. The catch? Yeah, manufacturing glass to those kinds of microscopic tolerances is insanely difficult and costly. Let's bring this deep dive full circle with Section 5, the fiber advantage. Time to see why all of this complex physics results in a network that just crushes old copper wires. Let's move to and see how this builds into real-world networking dominance. Sometimes, the absolute best way to grasp advanced tech is just to see it distilled down into straightforward bullet points, just like these original study notes outlining the core advantages. And this brilliantly illustrates the macro benefits we're talking about. The advantages over legacy copper wire are just staggering. Because these fibers are hair-thin, you can bundle massive amounts of them into a single cable for unparalleled bandwidth. They suffer incredibly low signal loss, so light travels way farther without needing to be boosted. And perhaps the biggest deal of all, because we are trapping light in glass rather than pushing electricity through metal, fiber is completely immune to electromagnetic interference. Plus, no one can easily tap into a glass beam of light, making it highly secure. So, as we wrap up this explainer, I really want to leave you with a thought. We just learned that the glass core of a fiber optic cable actually physically slows light down by about 1/3 of its maximum speed. As our world's thirst for instant data just continues to skyrocket, will this fundamental index of refraction eventually become the hard bottleneck of human connectivity? Are we going to have to invent a completely new medium to power the internet of tomorrow? Thanks so much for exploring the invisible backbone of our world with me today, and I'll catch you on the next explainer.